Go. Cool. All right. So let's see, what is today? The 4th? Yeah. All right. So we are going to be doing a couple things today. We're going to be talking about factoring by grouping along with factoring with a lead coefficient not equal to 1. So let's just go ahead and factoring in the GCF here. We'll just go ahead and do these two real quick. So what is a common factor with all three of those? 7. All right, so factor out a 7. That'll be d squared minus 5d plus 6. So we're going to have two numbers that will multiply to a positive 6 and add to a negative 5. This is the one that I messed up on the assignment. So that would be -2 and -3. So d minus 2 times d minus 3. And that'll be our answer for that one right there. Let's see, another one here. So this is where the multiplication chart might actually come in a little bit handy, because a lot of people might not know off the top of their heads that 39 and 42 have a factor of 3. And if you do know they have a factor of 3, not everybody knows that division off the top of their head, because that's not part of your normal 12 by 12 multiplication chart. So you're welcome to just find 39 on here and then figure out what two numbers multiply to equal it. Or, you know, if you want to go to 3 and then on your multiplication chart and then find 39, which is right here, that means 3 times 13 is 39. If you want to find 42 as well, it's just the next one, so 14. So we got 3j squared minus 13j minus 14. So what are our two factors that we're going to use here? $14 and 1, okay, and we have a negative multiplication, so that means one's got to be positive and one has to be negative. Which one's negative? The 14, yeah. So we got j minus 14 and j plus 1, or j plus 1 times j minus 14, either way. All right, so that's just our quick warm-up based on what we saw yesterday. Now, the next thing we're going to review today is taking a look at factoring by grouping, which I'm not 100% convinced every single person in here has learned. Maybe you did, maybe you didn't. Really what it turns into is figuring out a GCF for the first two terms only, and then figuring out a GCF for the second two terms only. And the hope is that the GCF between this set of 2 and this set of 2 is the same thing, because that will allow us to write our answer as the product of two binomials. So if we take a look here, just at the first two terms, what can you divide out of x to the third and 3x squared? What is it? X squared, yeah. So they both have two factors of x, so we're going to divide on x squared from both of those. And when we do that, underneath here, we're going to get x squared, and then in parentheses will be x plus 3. And I said it backwards. The GCF isn't going to be the same between the two sets. The leftovers inside of the parentheses should end up being the same. So if you take a look at these next two, what can you divide out of a 2x and a 6? 2. All right. So those both get divided by 2. And it is a positive 2. So after the parentheses here, you're going to write a plus 2 because it's within a larger expression. And so since it's positive, we write plus. Underneath here, the 2's would cancel, and we've got x, and then 6 divided by 2 is 3. So we end up with the same set of parentheses twice here, which is actually a very important part of this. Anytime you're factoring by grouping and you're trying to write your answer as the product of two binomials, both of those sets of the parentheses need to be the same in order for this to work. Because what you're going to end up doing is creating your first set of parentheses out of the GCFs, x squared plus 2. And then you're going to write that second set of parentheses in each of these as your second binomial. So that would be times x plus 3. And that's the answer. Anybody seen this process before? I'm sure some people have, but I'm also pretty sure that some people have not. Are there any questions about it if you haven't seen it before? Most of the time in Algebra 1, I have people asking, why is this not 2x plus 6? Right? Because we're putting both of those together here. And yet it still stays the same. And the reason has to do with the distributive property and how FOIL works. So actually easier if I stand up and show this. So if you think about how FOIL works, it'd be first, outer, inner, last. And if we do FOIL at the same time as we distribute up here, it ends up being the same. So we start here and we say first times first, that's going to be x squared times x, which here would be x squared times x. There's first times first. The outer would be x squared times 3, which up on the top would be x squared times 3. The inner is going to be 2 times x, which will be here. And then the last would be 2 times 3, which is here. So everything matches up 1 to 1 from the distributive property here and FOIL here, meaning this stays the same. All right, let's go ahead and look at the next one here. What can we factor out of x squared and y? What's that? 1, yeah. If we can't factor out a variable or some other number, you can always factor out a 1, which is actually what we need to do here. Because if you're writing a product of 2 binomials, that means you have to have values in each set of binomials. And so we're going to have to start with that. When you divide by 1, nothing changes. What are we factoring out of the second 2 terms? X. All right, so we factor out an x, factor out an x. And what happens here? So if I were to write plus x here, we end up with 1 plus y. That does not seem to work. And it actually doesn't work. Not the way we've done it anyway. So, does anybody have any thoughts on how to make this potentially work? Because it does work, but it doesn't work in the way that it's originally written up here. Because in order for this to work properly, we have to have the same set of parentheses twice here and here, which we do not have. So we can't actually just write this as a set of product of 2 binomials right now. So this doesn't work the way that it's currently written. So we can get rid of that. Do you see anything up here, or maybe a different way of rearranging these terms so that we could factor something out of both of them and not just be able to factor out a 1 from one of them and something else from the other? Any thoughts there? What about swapping around that x and that y? I mean, we're allowed to do that because addition is commutative. It doesn't matter what order we write the addition, and the answer is going to be the same either way, which allows us to swap those around if we want to. And in fact, we actually need to if we're going to go ahead and factor this one. So let's go ahead and write it as x squared plus x plus y plus xy. And then we'll actually have a variable that we can factor out of the first 2 terms, and then a variable that we can factor out of the second 2 terms as well. So for these first ones, we can factor out an x, which will give us x and then x plus 1. And then if we factor out a y from these ones, what do we have left in the parentheses? That'd be 1 plus x, right? And we just said a moment ago that you can flip around the order of addition and it doesn't matter. So x plus 1 and 1 plus x, that is the same thing. So when we write our answer, we'll just go ahead and move this x to the front of there and put the 1 after it. So we're going to say x plus y times x plus 1. That would be the answer to that one. So not every time you see 4 terms, you're going to be able to factor by grouping right away. Sometimes you're going to have to rearrange the order of some terms to actually make it work. So give A and B a try. See what you come up with there. I don't think you have to rearrange any orders for A and B to make those work, by the way. So Okay, let's have a look here. So let's see, with this first one here, actually, you know what? I might have been incorrect. I do think we need to swap around a couple things because there isn't a common factor between 2s and negative 27, is there? Yeah. I think these two in the middle should be swapped around. Yeah, this one, you don't have to swap anything. I didn't look closely enough at the numbers here with those ones. So yeah, you do need to go ahead and switch out. The two middle ones will be plenty to switch those out. So if you have 2s to the third minus 18s minus, actually, I'm going to make sure that things end up in the parentheses in the same order this time. So I'm going to say plus 3s squared and then minus 27 after that. That'll just make things the same order inside the parentheses if we do it that way. You'll end up with the same answer if you just switch the two in the middle. But all right, so here we can factor out a 2s. So that'll give us s minus 9 there. And then factoring out a 3, sorry, s squared minus 9. And then if we factor out a 3 from here, plus 3, that'll give us s squared minus 9. So we'll end up with 2s plus 3 times s squared minus 9. Now, this is kind of a funky one because we're not done yet on this one. This one is not yet done. Anybody know why? That's an S, by the way. My S's tend to be a little bit angular at times, so sometimes they look like 5s. Yeah. Anybody know why we're not done yet? Which one? The s squared minus 9? Yeah. This right here, we saw problems like this on our assignment yesterday. That is a difference of squares. If the first term and the second term are perfect squares, and there's a minus in between them, that's a difference of squares. So the answer to this one is actually going to be 2s plus 3 times s plus 3 times s minus 3, because s squared minus 9 factors to s plus 3 times s minus 3. We saw problems like that on yesterday's assignment. So there is that last little bit that has to happen to be completely factored for part A. So that one, a little bit tricky. And I apologize. Yes, you had to swap around a couple things because otherwise it wouldn't work. And once you do that, you have a difference of squares that you then have to factor at the end. So always be looking, it's kind of the moral of this mathematical story, always be looking to see if you can keep factoring even after you maybe think you're done factoring, because you might not always be done factoring. By the way, if there was another GCF after this that we could factor out of one of those sets of parentheses as well, we would do that. There isn't one, but if there was, we would. All right, for B, you do not have to swap anything around for B. So let's see, these first two terms here have a common factor of W. So that's going to be W here, and then we're going to get W squared, 3W squared plus 2. And in order to make sure that we get the same second set of parentheses, I'm just going to leave a gap, and I'm going to write 3W squared plus 2 in that set of parentheses before I actually factor out the GCF. Sometimes it can be helpful to do it this way, because if you think about what number you actually have to factor out here, it's not going to be 4. It's going to be what? -4, yeah. So it has to be -4 for this to work, because the only way to get from two negatives here and here to both of them being positive is to divide these both by a negative number. So it's not being divided by +4 or factoring out a +4, it's factoring out a -4. So what we end up with here is W minus 4 times 3W squared plus 2. And at this point, we're done. There's nothing else to factor after that. Neither of these is a difference of squares. There are no more GCFs, so that's our answer there. So in terms of factoring by grouping, that's what you're going to do. Factoring by grouping, you generally start with 4 terms, and you have to group them up in a way such that you can factor out a GCF, and you end up with the same set of parentheses after you factor out each of the GCFs of those two groups of 2 terms. All right, any questions on that before we look at the back? Okay, flip it over. So last part, has to do with what happens when you don't have a greatest common factor and yet you still have a number in front of x squared. So some other value for a other than 1. So in the last lesson, we factored trinomials with the form x squared plus bx plus c by finding two numbers that multiply to c and add to b. When the trinomial has a leading coefficient of a other than 1, things get a little bit more complicated. Honestly, not that much more complicated. There is a method. There's actually a couple ways to do this. You can end up creating a group of 4 and then factoring by grouping. That is one option. There's another option, though, that I actually prefer, and it's called the slip and slide method. And the slip and slide method has to do with slipping the value of a to the end and multiplying it by c. That's how we start off. So if you multiply 4 times 3 on the end, you end up with x squared plus 13x plus 3. No, plus 12, sorry. Gotta multiply it, plus 12. Okay. Then we're going to factor this like we would anything that we did yesterday. So we're looking for two numbers that'll multiply to 12 and add to 13. What would it be? 12 and 1, yeah, 1 and 12. So x plus 12 times x plus 1. We're not done, though, because if you FOIL this back out, you certainly won't get back to the beginning. You'll only get back to the previous step. So now the last part of this, we did the slip part, slip a to the end, multiply by c. The slide portion of this has to do with dividing both of just the constant terms in each set of binomials here by the original value of a. So 12 and 1 each get divided by 4. So you take the original value of a, and the constant terms in each set of binomials there get divided by that. Now, if it divides evenly, you just write the whole number. So for example, 12 divided by 4 is 3. So we get x plus 3. If it doesn't divide evenly, like this one here, this is where the slide part comes in. You slide the value, whatever the denominator is. If it's a fraction and it reduces and you still have a denominator, whatever that denominator is, that then slides in front of the x value in that set of parentheses, in that particular binomial. And so what we end up with is 4x plus 1 as our other set of parentheses. And at that point, we're done. If you FOIL that back out, it ends up exactly where we started. If you do the first times first, you get 4x squared. I'm just going to show this real quick. If you do the outer terms, you get 1x. Inner terms would be 12x, and last terms would be 1 times 3, which is 3. And if you add the 2 in the middle together, you're right back at 4x squared plus 13x plus 3. Now, there's another method for doing this, like I mentioned. You could start. Well, I think I'm actually just going to go ahead and keep this as it is. So we'll just go ahead and do that. If you have another method of doing this, by the way, if you learned another method a couple of years ago that you prefer to use, that's fine. There's more than one method for factoring. This is the one that I prefer to teach, so I'm just going to stick with that. All right, next one. Let's do this one, then I'll have you try the third one on your own. So you're going to take the value of a, 3, slip it to the end, multiply by 2. By the way, you don't have to draw the arrows if you don't want to. I usually do this, but if you remember the process and you don't want to do the arrows, you're not required to do that. So we got x squared minus 7x plus 6. So we're just going to factor that. What are the two factors that'll multiply to a positive 6 and add to a negative 7? Negative 6 and negative 1? Yeah. So x minus 6, x minus 1. All right, then we're going to take the original value of a, which is 3. Divide both of those numbers by 3. If it divides evenly, divide it evenly, which 6 divided by 3 is 2, so that'll give us x minus 2. However, if it doesn't divide evenly, or if it's a fraction and you can reduce the fraction, if there's still a denominator, that denominator slides in front of that particular value of x. So we'd get 3x minus 1 there. And that will be our answer. And you can always multiply it by, back out using FOIL, and you should always end up right back where you started. Any questions on that process? Cool. Try the last one on your own. So this is what the process would look like without the arrows and actually showing the division and all that. So go ahead and take a look there. 2x minus 7 times x plus 1. And again, you can always double check your work by foiling it back out just to make sure you got it right. All good? Cool. So that's it for today's lesson.